Let us now get back to the single object allocation domain, the reason for which we discussed some of the results from convex analysis. And we are going to discuss about monotonicity and a very important result of the single object allocation, which is known as the Myerson's lemma. Now for that we are going to define a property which is called the non-decreasingness of an allocation rule. So what does it mean? So it means that if for player I the valuation of that player I is increasing, then the probability of allocation of the object to that player cannot decrease. So it is essentially saying that suppose player I had two types, SI and TI, where where TI is strictly greater than SI. Then this inequality which says that the allocation probability of player I when player I's type is TI and the other players are always holding on to the same type profile, then this allocation probability will be non-decreasing. So that is the whole idea of the allocation rule being non-decreasing. Now equipped with this definition of non-decreasingness, we can now state the result of Myerson. Here it goes. So it says that suppose we have a type set for player I, which is the interval between 0 to bi. And the valuations are always in the product form. That is something that we have assumed in the very beginning. Then the allocation rule, which maps this type profile into the set of allocations, and the payment rule are DSIC if and only if. So this is a necessary and sufficient condition. So these two properties hold. Which the first property says that f is non-decreasing, so the non-decreasingness that we have just discussed before, and payments are given by a very specific formula. So this is called the Myerson payment formula. What does it say? So you have one constant, so which is at ti equal to 0, and then you have this term. So you are first multiplying this type ti with the allocation probability, and then subtracting the integral of that fi, that allocation probability, integrating between 0 to ti. And everywhere you are holding the type of the other player to be fixed. So because this is defining the payment for player I, and for all the players except player I, their types are getting fixed. And this holds for all the types of player I, all the types of the other players, and also for all players. So this is a necessary and sufficient condition, a mechanism which gives both the allocation rule and the payment rule. If it has to be DSIC, it must satisfy these properties, and these properties also imply that this is DSIC. Now it's very natural to ask the question. We have seen a very similar result in the context of quasi-linear domains called the Roberts theorem, which also says that if you have an unrestricted valuation domain, then the allocation rule that you can implement is of affine maximizer. So the first difference is that was a deterministic result. So the social choice function that was being implemented, or the allocation rule that we are implementing, is a deterministic rule, argmax, while this is a randomized rule. But even beyond that, the Roberts theorem is essentially giving a functional form. It is giving an affine maximizer as the outcome. While Myerson's result, even though they are dealing with a very specific problem of single object allocation, it is giving a more implicit property in the sense that it is telling that the allocation rule must be non-decreasing, but it is not mentioning which kind of non-decreasing rule. And so if the function has a particular value of allocating this object among these players, then at some other point you should also maintain certain monotonicity. But it's more like a little implicit description, while Roberts is directly giving you a functional form. But sometimes it is more useful to have a functional form. So therefore Roberts' result might be of use in certain settings. Nevertheless, we'll see that this result has a very important implication in terms of maximizing the revenue. So let us get into that. So first, let us try to prove the forward direction of the Myerson's result. Which then says that this function f comma p is DSIC. So we'll have to show that it satisfies those conditions 1 and 2. So for that, we can actually write down the utility of player I at these two type profiles. So ti t minus I, we know that this the valuation is in this product form. The utility when the allocation rule is of course f, and therefore this is going to be the allocation to player I, and you multiply that with ti, take the payment out, and that is going to be the utility for player I. And similarly, when the type of player I changes to si, all that changes is these 2 points and this point here. Now, since f comma p is DSIC, then it must hold that if you write the same expressions for this utility, this term should be at least as much as this. So where you can see that the player I's true type is still the same, ti, but what he reports, because this function f and pi has to be dependent only on what has been reported. So this should be f of I here and here as well. So this term, so when player I actually misreports his type to si, then this inequality should hold. Now what we are going to do is we are going to add and subtract one term, si, fi of si comma t minus I, right? So this term, if you add to this expression here and subtract, then you can actually write it in this form. So the first term will be si fi of si t minus I, and then you have the second term, and then you write so this terms which has been shown in white is already coming from the previous step, and this one that is shown in blue is actually being added and subtracted. Now what does this mean? So if you look at these two terms together, this and the first one, you see that this is nothing but the utility of player I when the type profile is si t minus I. So we can collect these two terms together and write it as utility of si t minus I, and the other term is fi si t minus I multiplied by ti minus si. And the reason that we have written it in this form has a special meaning. So now if you fix this t minus I, the types, the valuations of all the players except agent I, we can define, let's say, a function g of ti that is going to be the ui. So this left hand side here. So therefore g of si will be the first term here, and we can also write f of phi of ti, which is fi of ti t minus I. Now this is very much reminiscent of the convex function and its subgradient that we have defined in the previous module. So now we can we can rewrite the previous expression, the equation 1, in the following way. And you know that this expression, this inequality of 1 holds for all possible values of si, t minus I, ti, etc. So therefore, for all those values, we can actually write this in an equivalent way. So when t minus I is held fixed, phi of si is the subgradient of g at si. So this is something that we have defined in the previous module. So we are just using that fact. So this is a subgradient. Now, in order to apply those lemmas that we have proved for convex functions, we will first have to show that this function g is indeed convex. So let us do that. So let us show that this function g is convex. Now, in order to do that, let us pick two arbitrary points, xi and zi, both of which are in this type set capital Ti, and we are going to define a convex combination of these 2 points, where lambda belongs to 0 and 1. You take the convex combination of these 2 points xi and zi and define that as yi. Now, because of the property of dominant strategy incentive compatibility, you can actually write this this term for both xi yi and zi yi. So if you just replace the corresponding ti with xi and zi, then what you will get is some expression like this. And in both these cases, on the right hand side you will have g of yi, and the subgradient will also be at the same point, but this terms will differ. Now what we are going to do is to multiply the first term with lambda and multiply the second term with 1 minus lambda. We just have to be a little careful because when lambda is either 0 or 1, this the other inequality actually disappears, so it does not really matter. For all the other cases where lambda is neither 0 nor 1, we can actually write this, do this multiplication and write this. Now what is happening on the left hand side? This is very simple. It is getting multiplied. The first one is getting multiplied with lambda, the other one is getting multiplied by 1 minus lambda. So therefore the left hand side is quite obvious. On the right hand side, because these are both the same numbers, g of y, so they actually add up to g of yi. For phi of yi, we have inside this lambda of xi plus the 1 minus lambda lambda of z of I minus y of I. Now you see that we have chosen yi in such a way that that is the convex combination of these two things. So therefore this expression, after you have summed it up, it is going to be equal to 0. So therefore this whole term actually disappears. So all that you have on the right hand side is this g of yi. Now you can also expand this yi, and that is the definition of a convex function. This inequality says that g is actually a convex function. So we are essentially in a good position now to apply the lemmas 3 and 4 from the previous module. Remember, the lemma 3 was going to say that this subgradient, we have a convex function and we have a subgradient. This is going to be a non-decreasing function. So it says that so what was phi? It was fi, the argument was ti, and t minus y was held fixed, and this is going to be non-decreasing. So therefore that proves the part 1 of this implication of Myerson's result. For the second part, we will have to prove that this is the payment formula. So for that we are going to use the lemma 4, which gives you a specific integral formula. So this we are going to apply to g of 0. So we are going to take the initial point to be equal to 0 and take the integral from 0 to ti. Now the rest of the thing is just manipulation of these terms. You just expand this out. Whatever was the definition of that was the utility here, and this was the subgradient was the allocation probability of player I. And then if you expand this out, what we will get is essentially the expression here. So this is nothing, I mean, that we really need to go into in detail. Rather it's just a mathematical manipulation that gives you the final expression for this payment for player I. So that's done. The forward direction is done. The forward direction shows that if you have a mechanism which is DSIC in this single object allocation domain, then it must, the allocation rule must be non-decreasing, and also the payment should be given by this formula. Now we have the reverse direction. So we have those two equations at our disposal. We'll have to show that this mechanism is indeed DSIC. Now we are going to do it by this proof by pictures. Of course there is an alternative way of showing it analytically, but the proof by pictures is much more elegant and easy to understand. So what are we trying to do? So we know that we have this particular formula for the utilities. So we are going to show that if player I has this type of TI, where other players are reporting t minus i's, and he is reporting it truthfully versus untruthfully, so this difference should be non-negative, right? So that is the requirement for truthfulness. How can we show that? So first let us look at what this payment formula, and for this for simplicity, let us assume that this 0th point, so this payment part is actually 0. Even though it is not equal to 0, the proof works. the picture will be a little different in that case. So for simplicity, we have assumed that this is equal to 0. So then what is the meaning of this payment formula? So notice that the first one is actually, so, and let us assume that this is this curve is actually a monotone curve, non-decreasing curve that is given, and the fi of ti. So suppose, so in all these cases we are actually fixing this t minus I, and the x-axis of this plots are denoting the type of player I. Now if player i's type is ti, and then this the payment function is going to, so remember that ti is the true type of player I. Now player I can either report ti truthfully or maybe misreport, either say something higher than ti or smaller than ti. So when it reports ti truthfully, then this when you compute this value, it is just multiplying that ti, so this ti multiplied by the value of f of ti minus I, so which will give you this whole space, the whole dotted line that has been shown here. Now what you are subtracting out as in the part of this payment, so that is the integral from 0 to ti, so 0 to this point ti, you are integrating out this part. So essentially what is below this curve, this green shaded region, is being subtracted out. So therefore all that you have in this rectangular space is this yellow shaded line. That is the payment for player I. Let us just remember that whenever you report something, player I is reporting something, this part, which is the area under the curve looking from the y-axis, is essentially the payment for player I. Now let us look at two different contexts. In one case, so the first case is that player I is over-reporting, is reporting SI which is larger than TI. What happens? So you notice that the payment is going to be only changing. So of course the allocation will now be Fi of Si T minus I. Right? So that is because it has reported SI. So therefore this value is going to be the allocation. Okay, so even before that, so since the total utility, so Ti was the type of player I, and the allocation in the previous case was Fi of Ti. So therefore this the whole term here was the valuation minus this was the payment. So therefore this green shaded region is actually the utility of player I. Okay, so we are going to compare that with the two other cases. So here the allocation is this much. So the Ti multiplied by Fi will still be this rectangular space here, and therefore so if you look at the total utility of player I, that is still going to be Ti multiplied by this larger number, right? So now the allocation has actually gone up to that point, so therefore its valuation is still this region here. Now the problem here is it is actually extracting a payment which is even larger than that. So if you look at this is the payment that will be extracted because the player has actually reported SI. So the area under this curve is subtended on the y-axis is going to be the payment. So if you subtract that out, you have this original utility that you were getting when you were reporting it truthfully, minus this region, this red region, which is now getting negative. So you get less than what you were getting earlier. And similarly, when you report something smaller, so suppose SI was smaller than TI, then the allocation will be f of SI T minus I. So that is going to be a little smaller thing. So the valuation that player I will get is this smaller rectangle here. And the payment that will be collected is also this one. But what you actually lose is the green part, which could have been this large. This amount you are actually losing. So whether you report your type to be smaller than the true type, or larger than the true type. In both these cases, you are actually getting utilities which is smaller than this green value, which is the utility when you are reporting it truthfully. So that essentially tells you that whenever you have this payment formula and together with the fact that f is not decreasing, the utility will always be maximized when you report your types truthfully. So that actually completes the proof. So an alternative way of mentioning this is that this allocation rule in a single object allocation is implementable in dominant strategies if it is not decreasing. But the Myerson's result is saying more, that the payment formula must be of that form. No other kind of payment can implement this. Alright, so that completes the proof of a very important result, namely the Myerson's result for single object allocation.